Is Yellowstone going to erupt? New research reveals the supervolcano is venting, not building toward an explosion. Groundbreaking study identifies stable, gas-venting magma cap beneath Yellowstone, lowering eruption risk and advancing subsurface imaging techniques. Beneath the steaming geysers and bubbling mud pots of Yellowstone National Park lies one of the most closely monitored volcanic systems on Earth. A new study published in Nature offers critical insights into how this immense system behaves and what may be keeping it from erupting. A team of researchers from Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas has discovered a volatile-rich magma layer just 3.8 kilometers beneath Yellowstone's surface. This cap-like layer acts as a pressure release valve, allowing gas to escape while stabilizing the magma reservoir below. Using state-of-the-art controlled source seismic imaging and high-resolution computer modeling, the team found that the magma reservoir is actively venting gas, but remains structurally stable. Their findings not only reduce concerns over an imminent eruption, but also mark a significant step forward in subsurface imaging techniques. This reservoir hasn't shut down, it's been sitting there for a couple million years, but it's still dynamic, said Brandon Schmant, professor of Earth Environmental and Planetary Sciences at Rice University and co-lead author of the study alongside Chenglong Duan, a postdoctoral research associate. The research was supported by the National Science Foundation. Until now, estimates for the depth of Yellowstone's magma system ranged from 3 to 8 kilometers, leaving much uncertainty about its current state. That changed when Schmant led a high-resolution seismic survey of the caldera's northeastern region. Using a 53,000-pound vibrosis truck, typically used in oil and gas exploration, the team generated small, controlled seismic waves. These waves bounced off underground structures and were recorded by more than 600 temporary seismometers, revealing a sharp boundary at about 3.8 kilometers deep. The motivation behind my research is to push structural seismic imaging beyond the limits of traditional methods, Duan explained. Using a wave equation imaging technique I developed during my Ph.D., we captured one of the clearest images to date of Yellowstone's magma cap. That sharp seismic reflector pointed to a distinct zone of partially molten rock interspersed with gas bubbles, what the researchers describe as a volatile-rich cap within porous rock. Duan and Schmant's models suggest the cap is composed of silicate melt and supercritical water bubbles, occupying about 14% porosity, with half of that space filled by fluids. In volcanic systems, rising magma releases gases like water vapor and carbon dioxide, forming bubbles that can contribute to explosive eruptions. However, Yellowstone's current state appears relatively calm. Although we detected a volatile-rich layer, its bubble and melt contents are below the threshold, typically associated with imminent eruption, Schmant said. The system seems to be efficiently venting gas through tiny cracks and channels, consistent with Yellowstone's abundant hydrothermal activity. Schmant likened the venting system to steady breathing, with bubbles rising and releasing through porous rock, acting as a natural pressure release mechanism. Conducting the fieldwork was no easy feat. The research took place during the COVID-19 pandemic, and had to comply with strict park regulations. The Vibrosis truck could only operate at night and from designated roadside turnouts. Collaboration with Jamie Farrell, a geophysics professor at the University of Utah and a key operator of Yellowstone's seismic network, was instrumental in executing the project. Interpreting the seismic data proved equally challenging. Yellowstone's complex geology caused significant signal scattering, making it difficult to detect clear reflections. But Duan and the team persisted, eventually refining their analysis using a technique called STA-LTA, short-term average/long-term average, to enhance coherent seismic signals. When you're working with data this noisy, it's easy to feel discouraged, Duan said. But that's when creativity becomes essential. We adapted our approach until the story hidden in the numbers became clear. This discovery not only enhances the ability to monitor Yellowstone's volcanic activity, but also sets a new standard for imaging complex subsurface systems. Future studies could use this technique to monitor changes in melter gas levels, potential early warning signs of unrest. Beyond Yellowstone, the implications of the research are far-reaching. The methods used here could be applied to geothermal energy development, carbon storage, natural hazard assessments, and broader geological exploration. Being able to image what's happening underground is critical, not just for volcanoes, but for understanding energy resources and climate solutions, like carbon sequestration, Schmant said. This study proves that with persistence and innovation, we can see through even the most complex geologic puzzles.